Let's talk about one of the most important pieces of technology you've probably never even heard of. It's called the PID controller. And really, it's like this invisible brain that quietly and, well, perfectly runs so much of our modern world. I mean, you've definitely experienced this, right? You set your cruise control, and the car hits a hill and needs more gas, or it goes downhill and needs less. But somehow, the speed stays locked in, almost like magic. How in the world does it know exactly how much to adjust and when? Well, that little bit of magic is precisely what we're going to break down. And this brings us right to our first big idea, the core challenge that all of these systems face, what we can call the constant correction problem. And look, this isn't just about your car's cruise control. Think about the thermostat in your house, working to keep the temperature just right, or a huge factory that needs to keep the level in a tank perfectly steady all day, every day. There are just countless systems all around us that need to stay on target, even when things are constantly changing. Okay, this diagram, it gives us a perfect picture of the problem. You've got oil flowing in, maybe at a totally unsteady rate. But the goal, the whole point, is to keep the level at that ideal set point. So to do that, a controller is constantly measuring the level and then deciding exactly how much to open or close that outflow valve. It's this continuous loop, right? Measure, decide, act over and over again.
So how do we solve this? How do we make that loop smart? Well, this brings us to our next section, Meet the PID Controller. This is the elegant and, frankly, powerful solution to this very problem. And it's honestly not an exaggeration to say these things are everywhere. I mean, they're the real hidden heroes. They're stabilizing our power grids, running massive manufacturing plants, guiding rockets into space, and even steering giant ships across the ocean. They are truly fundamental to how things work.
Now, to really get this, we need to wrap our heads around the idea of a control loop. It's a really simple but powerful concept. So you have a target, that's your set point. Then you have the actual current measurement, that's the process variable. And the difference between them, that's the error. The controller's entire job, its whole reason for being, is to look at that error and make a correction to drive it down to zero. Here, we can see that whole loop in action. An operator sets the target temperature, that's our set point. Then a sensor measures the actual temperature in the tank. That's our process variable. The controller just subtracts one from the other to get the error. Then, using its special PID logic, it calculates a brand new position for the gas valve. It's a constant, never-ending cycle of feedback and adjustment. So what exactly is this PID logic? What do those letters, P, I, and D, actually stand for? Well, it all comes down to three very distinct strategies, all working together for one single goal: zero error. Probably the best way to think about it is like a team of three specialists. You've got one specialist who only cares about the present, another one who remembers everything from the past, and a third one who's always trying to predict the future. And together, they create this perfectly balanced response. All right, let's start with P for proportional. This is the impulsive, right-now specialist on the team. Its rule is super simple. The bigger the error is at this very moment, the bigger the response. So if the system is, say, 20 degrees too cold, it yanks the gas valve way open. If it's only 2 degrees too cold, it just opens it a little bit. It's a purely proportional reaction. But here's the catch with being only proportional. If you make it too aggressive, you turn up that K value to get a really fast response. The system just flies right past the target. It overshoots, then it overcorrects going the other way, and you end up with these wild, unstable swings. Not what you want at all. And that brings us to our second specialist, I for integral. This one is the team's memory. It doesn't just look at the error right now, it looks at the total accumulated error from the past. It's always asking, okay, how big has the error been, and for how long has it been there? So the integral's main job is to hunt down that tiny, nagging error that the proportional controller often just gives up on. You know, that last little bit? Even if the error is small, the integral term just patiently builds up its response over time until that error is completely, totally gone. It's what guarantees perfect accuracy. And finally, we have D for derivative. This is the team's futurist. It doesn't care how big the error is now or how big it was in the past. It only cares about one thing: how fast is the error changing? It's basically predicting where the error is headed. And it acts like the brakes, right? It applies this damping force to slow the system down as it gets close to the target so it doesn't just fly by. You can really see the effect of the derivative term here. See, without enough D action, the system overshoots and just rings like a bell. But as you add in that derivative control, the approach gets so much smoother. It prevents that overshoot and lets the system settle on the target quickly and gracefully. Okay, so we've got our three specialists: the reactive proportional, the persistent integral, and the predictive derivative. The final, and maybe most important piece of the puzzle is getting them all to work together. This process is called tuning. This slide shows you exactly what engineers are looking at when they tune a system. Yeah, they want a fast rise time to get to the target quickly, but they absolutely have to minimize that transient overshoot. And most importantly, they're aiming for the shortest possible settling time. That's the time it takes for the system to stop wobbling around and finally stabilize. In getting there, well, it's a delicate balancing act. It's a game of trade-offs. If you crank up the proportional gain, the system gets faster, but you risk those wild oscillations. If you increase the integral, you'll wipe out that final little error, but you might make the initial overshoot even worse. And if you add more derivative to dampen that overshoot, you might just slow the whole system down. So ultimately, there's no single best setting. The real magic of PID control is in the tuning, in carefully adjusting the strength of each of these three actions to find that perfect, harmonious balance for whatever specific system you're trying to control. It really all just boils down to this. P is for the present, I is for the past, and D is for the future. Three really simple ideas, all working together in a continuous feedback loop. And that's the beautiful secret of PID control. It's not some impossibly complex, crazy algorithm. It's an elegant, three-part logic that's just based on the present, the past, and the future. This simple code is what brings precision and stability to our complex, sometimes chaotic, and pretty amazing technological world. It kind of makes you wonder, what other invisible systems are out there, quietly running everything?